title is Exponential Growth Curves. So all the functions that you guys just graphed on your calculators were exponential. Remember, they fall into that category because the x is in the exponent. That makes them exponential, okay? But exponential functions have two separate categories, and knowing the two categories is just going to help you graph them faster and know what the original shape looks like. One category is growth, and it means that as the numbers get bigger, your curve grows or gets further and further away from the x-axis. The other category is decay, okay? And it means that as you plug in bigger numbers, you get closer and closer and closer to 0. So for example, 2 to the power of x is a growth graph, because as I plug in bigger numbers, it gets further and further away from the axis. Even if you flip it over, it's still growth because it's still getting further and further away from the axis. When the base was 1/3, when your b value was 1/3, this is decay, because as I plug in bigger and bigger numbers, it just gets closer and closer and closer to the axis. Okay? Will it ever reach 0 exactly? Like, is there a number, an exponent that you can put on 2 that makes it equal to 0? So what's anything to the 0 power? 1. If we use negative powers, it just makes it a fraction. Fraction powers just take radicals. So is there any exponent that says, oh, it turns stuff into 0? No. We talked about this when we did our logarithm problems, right? That's why certain things were like undefined. So you never actually reach 0. It's this weird idea. Like, you get really, 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 really close to it, but there's no exponent that can actually reach 0. So that means in our parent functions of these exponential growth curves, there's always an asymptote across here at 0. Now remember, this is the parent function, okay? The equation for these means they'll always have just some number being raised to the power of x. So in the investigation that you guys just did, you had 2 parent functions on here, and they're slightly different, which is a complication from before. There's not one parent function. You actually have to think a little to make your graph for your parent functions, okay? But both number 1 and number 7 would be parent functions of exponential growth graphs, okay? Even though they were different. So one of them said 2 to the x, and one of them said 5 to the x. But both of these graphs had the shape that as you plugged in bigger numbers, they got further away. That makes them parent functions for exponential growth, because they don't have any extra stuff being added, subtracted, or multiplied to them, and they follow that shape. But they wouldn't both be the exact same, okay? So when you make a parent function graph for whatever function it is that you're working with, there is one thing that's the same. No matter what my base is, whether it's 2 or whether it's 5, what happens when I put 0 in as the exponent? I get 1. So the one consistent point that all my parent functions will have is that when I plug in 0, I get 1, because anything to the power of 0 is 1. So when I plug in 0, I get 1. That's a point on my graph. Okay? So the parent functions for exponential growth, they're just going to go like that. Okay? But you guys know when you stretch and compress and stuff, you can't just have one point on the graph. You need some other points around it to be able to stretch them and compress them appropriately. That depends on the actual function. So for example, if my actual function was y equals 2 to the x, my parent function would generally look like this graph. It's going to have all this shape on it, okay? So it's going to have this asymptote across here like this. It's going to have this point at 0, 1. But where exactly the other points are totally depends on the number right here, okay? Like if you put 1 as the exponent, what's 2 to the first power? Not the hardest question you're going to get asked today. 2 to the first power is 2. Okay, so in other words, if you plug in 1, you're getting 2. What about if I plug in negative 1? What's 2 to the negative 1 power? 1/2. So when I plug in negative 1, I'm getting 1/2. Those are the exact points that belong on that graph. It has this shape, right? But I need those exact points to be able to do the stretches and compressions. If I was starting a problem that had 5 as the base, my graph would look slightly different, okay? Would still have the asymptote. Still, when you plug in 0, you get 1. But then I have to be a little more careful. What happens when I plug in 1 to this equation? What's 5 to the first power? 5. Okay, so when I plug in 1, I get 1, 2, 3, 4, 5. Okay? And when I plug in -1, what do I get? 1/5, right? Like flip it over. They don't look much different. The shape looks the same. If you just glanced, you'd think they were the same. But where I plotted the points is a little bit different. So whenever you're graphing an exponential function, know that you're going to have this general shape. But when you start it, okay, when you start with the parent function, you actually have to plug in a couple numbers to see where these points end up, because it'll be different for each parent function that you have. If it was y equals 3 to the x, the side points would be in slightly different places. Does that make sense to everybody? So you'll have this general shape, but you're going to have to do a little bit of thinking just to get the very first graph before you do any stretches, compressions, or anything like that. Okay? All right, and then real quick before you leave, write down a decay graph too. So this one is called an exponential decay graph. It's like what you guys had with 1/3. Okay. Its equation is the same, okay? But in this one, your base is smaller than 1. The example that you saw on your handout of this was when we did like 1/3 to the power of x, okay? Still, anything to the 0 power is still 1. So you still have this point at 0, 1, okay? But remember, this one behaves differently. The bigger exponents you plug in, you actually get smaller results because of the fraction. So this curve is going to go this way. Okay? But again, if you're starting a graph and the graph is based on this equation, you're going to have to be a little more specific. You're going to put in your asymptote, you're going to put in your point at 0, 1, and then you have to do 2 calculations before you can start anything else. What do you get when you plug in 1 as an exponent here? So 1/3 to the first power is 1/3. And 1/3 to the -1 power, we would get 3. I need those exact points in order to start moving stuff and stretching and compressing. So there's like the idea of what the graph looks like, but the extra work that we never had to do before was actually figuring out new points every time we started a new parent function graph. Okay? So tomorrow what we'll do is we'll take actual examples of this now that we know the basic shapes. We'll make the parent function, and then we'll do all the transformations, reflections, okay, shifts up and down, stretches and compressions. So tonight, you guys, no homework on exponential functions, but I'm going to post solutions to your 3 worksheets that you worked on. So check those so that when we get to the solving part, you know how to do them.